So now that we know a little bit about what neural networks are and how they are constructed, we're going to adapt them to do classification problems. Okay. For now, we will use MATLAB's deep learning infrastructure, and then we will touch upon Python's deep learning infrastructure later on. But of course, what follows, the discussion will generalize to other frameworks too, and so on. So the discussion itself is pretty general, but we will just see an example of it in MATLAB, and then, like we said, perhaps Python later. What I want to do first is to recall multi-class softmax logistic regression. Okay, so this is something that we did 2-3 weeks ago now for multi-class regression. And then first implement this thing, which we've already examined in some sense in detail, but implement that as a neural network, right? So you can think of this as kind of a neural network. And of course, doing multi-class logistic regression with softmax has some limitations, as we saw. It could only get so much accuracy, I don't know, 80 something accuracy when you had 10 classes. So it is far from amazing. So it has limited accuracy. So what we will do is once we've constructed a neural network that does that, we will add additional neural network layers to get greater complexity of the function approximator, and then use that to get more accuracy. Okay, so that's going to be what we're going to do. And what I'm going to do is first we will talk through this write-up, and then I will switch to MATLAB and walk through the MATLAB implementation of this. Okay, so let's recall multi-class logistic softmax regression before we do neural networks. Let's say we have an image, for instance, some input, which is Q, and it's got, if it's an image, let's say it's got n pixels, it's n dimensional. And if you recall in MNIST, it was 784 or something. So anyway, so Q is a single input, okay, which has got n dimensions. The output belongs to one of m classes. For instance, in MNIST, m was equal to 10 different classes. Same case in CIFAR 10 and so on. So what we're trying to do is construct a function that takes 784 numbers to give you potentially one number which belongs to one of these 10 classes, or 10 numbers which are actually probabilities for each of these classes. Okay, so what we are going to do is take an input, an image, let's say, which is 784 numbers, and actually give 10 numbers or m numbers, which are probabilities for that input belonging to each of those m different classes. Okay, so and then we're trying to approximate that function via a neural network. That's the idea. Okay. But before that, we are going to see how the old softmax regression works. So when we have Q as an input and these outputs, what we first do is construct m linear functions, zi of Q, and for each class. If you have 10 classes, we'll have 10 zis. And each of these zi's will have different coefficients a0 till an. So zi is defined as a0 plus a1 q1, a2 q2, etc., or q1 q2 q3, etc., or the individual elements of q. And immediately notice that this is just a linear function of q. It's got, in the neural network language, a bias term and the weights, where the weights are a0 and an, right? So, okay. That sort of looks like the first step of a neural network, where zi is kind of implementing a linear function of all the inputs. And then once you have all z1, z2, z3 until Zm. So there are as many Zi as there are classes on the output. Once you have all the Zi, what do we do in softmax regression? In softmax regression, we apply the softmax functions on Zi, okay, which takes all the Zi's. So Z contains Z1, Z2, Z3, etc. And then you say softmax, and you get the probability P1, P2, P3, etc. Till Pm or P10 for each of the M classes. Okay, so you go from Q to Zi and Z to probabilities that the image belongs to each of the classes. So that's what we do in softmax regression. And then this is the actual function that goes from input to output, the output being probabilities. Of course, to train the function or learn an appropriate function, we tune all these biases and weights A0, A1, A2, etc. for each of the different Zi's. There's going to be n plus 1 times m unknowns. We tune all those things so as to minimize the so-called cross entropy loss or log loss, which sort of finds the distance between these probabilities and the outputs. Okay, and this we solved using fmin-nunc or stochastic gradient descent or whatever in the past. Okay, so that's softmax regression or multiclass regression. We already said this kind of looks like what goes in a neural network, these linear things. So this is how we would represent. So we can represent all the stuff using something that looks like this. You have an input layer, which is Q1, Q2 till Qn. This whole thing is one image. Q1 is the first pixel, Q2 is the second pixel, etc. Right? One image. And then those give rise to Z1, Z2 till Zm. And I'm representing via these neurons here this linear transformation. Okay, this linear transformation is represented by a single neuron, and there are m such neurons. And Q1, Q2, Q3, etc. all input into this neuron to produce Z1. So there's going to be A0 plus A1, Q1, A2, Q2, etc. until Qn to produce Z1. And then all these inputs come together to produce Z2, Z3, Z4, each with a different sets of weights and biases. Okay. Because all of them contribute to each output, we would call this fully connected. In other words, all neurons here are connected to all neurons here. It's called fully connected or all-to-all connections, ALL to ALL, all-to-all. Okay. Now, Z is just a linear function of the inputs. Excuse me. Which means that this is not your regular neuron. It's got this linear transformation, but it doesn't have the activation function, right? So we usually have this activation function, which could be a binary step or a threshold activation or a logistic activation or a ReLU activation. We don't have all that. This Z is just a linear function, okay? So it's a very simple kind of neuron where the activation function is just a line of slope 1, okay? So that's how you get the Z's. It looks like this. Fully connected layer, no activation function, and then all the Z's are transformed by the softmax function, which we can call perhaps a softmax layer to get the P's. Okay, P1, P2, which are the probabilities. And each of these P's depend on all the Z's. Okay, so we have an input layer, which are all connected to purely linear neurons to give the Z's, which go into a softmax layer, softmax function, which give you the probabilities, the outputs, okay? Outputs that, given an input, it belongs to one of these M classes. So we can, so it's a function from Q to P, we can abstract this function as f of q, where f basically is the neural network, p equals f of q. And then we can train this neural network, which is finding all these coefficients, a0, a1, etc. Given an image, f acts on it to give you the probabilities. You can take the probabilities and the actual output in the data. Using those things, you can compute the so-called loss function, which tells you how bad the model is. And you can minimize how bad the model is by tuning all these parameters using optimization, namely stochastic gradient descent is what we are going to use. And by using stochastic gradient descent to tune all the a0s, a1s, a2s, etc., we can make this function do a better job of predicting the data y. Okay, that's the idea. So that's if we want to literally implement softmax regression or multi-class stochastic logistic regression as a neural network. We haven't done anything new. We've just reframed softmax regression in sort of like a neural network-like framework. And so this is not going to change anything because this is literally logistic regression or softmax regression. It's not going to dramatically improve anything. What improves the performance is basically take this, instead of directly connecting to Z, we add multiple layers here. So we add more hidden layers, more neurons, potentially many more neurons between Qs and the Zs. And these many more neurons essentially allow the function approximator to be more flexible, be able to approximate a more and more complicated function. And then if we tune the biases and weights for each one of these neurons, and there could be thousands of neurons here, we could make the outputs be more representative or better fit to the data. That's the idea. Okay, so these layers, I say, could be fully connected layers where all the Qs connect to all the neurons here, and all these neurons connect to all the neurons, all these neurons connect to all the Z neurons, etc. And these neurons will need to be nonlinear. In other words, they will have a linear part and a activation function so that they are nonlinear, and that's how you will actually be able to approximate more complicated functions. Okay, if you just have the linear neurons here, that only takes you so far. Having these nonlinear layers allows you to make things more sophisticated. Okay, so they in the first example, we will just make them fully connected layers because that's simple to understand. Basically, all neurons are connected to all neurons and so on. But what we will change to eventually is what are called convolutional layers, which basically mean that not all neurons here are connected to not all neurons here. Some neurons are connected to some neurons, other neurons are connected to other neurons, etc. So it's more limited in a very systematic manner. So we'll talk about that and why that's useful and so on. That'll be a later lecture. Okay, so that's it. I have another remark here that says that batch normalization is something that we will do in between layers to improve convergence. So I'll just talk about that when we do the MATLAB demo. Okay, so on to MATLAB demo, where we'll first do this, literally implement logistic regression as a neural network, and then add additional layers to substantially increase the accuracy.